recording, and tonight we are going to finish up Module 2. And the last topic in Module 2 is confidence intervals and sample size estimations. There are really three different forms, not really forms, three different types of confidence intervals. And we are going to try to talk about all three types tonight. Okay. So I'm going to share my screen. I have posted in D2L the new PowerPoints. Okay. I have posted the new PowerPoints. So we're going to begin with confidence intervals and sample size estimation. And this particular presentation, we're going to look at kind of what is a confidence interval, and then we're going to specifically look at and focus on where we are given or know the population standard deviation. Okay, so I didn't realize this picture was still drawn here, so let me erase it so I can redraw it and explain it as I go. I got a better option. Cut. And then insert. All right. So I just put a new slide in there. I want to try to help you see and understand what it is we are about to begin talking about. If you go back to the beginning of the course, and it may even require that you go back to the beginning of Stat 1401, we learned that there were two different branches of statistics. Okay, one of the branches is called descriptive. Descriptive is the adjective form of the verb describe. And so in the area or in the branch of statistics, we are simply trying to describe the data set. We are simply going to state or provide the facts with no assumptions. I'm going to be able to tell you how many you had in the sample, what was the mode, what was the median, what was the minimum, what was the maximum. So we begin to just describe the data set. Again, providing just the facts without any assumptions at all. And we've been doing that, and we looked at that in the second lesson of Module 1. Okay, we talked about the area of statistics called Descriptive Statistics. That was in the first unit, and it was the second lesson. And when we did that, we would calculate those descriptive statistics, the mean, the median, the mode, standard deviation, range, variance, all of those different measurements. And we would come up with an answer. But the answer we had was a single value. And in statistics, we didn't talk about it then, but the fact that we were using a single value to represent those measurements, whether it was the mean, the median, the mode, or whatever, it's called a point estimate. Okay, so a point estimate is a single value that represents that particular measurement. Okay, and there's nothing wrong with a point estimate. And we'd like to be, think that we're correct. But with a point estimate, if you think about it like a target, okay, that's like you've got this little bitty dot right in the center, your little bitty bullseye, and you're saying that your mean, your median, your mode is exactly that one little speck on the target. So that's a little bit challenging. Again, it's not wrong to use it, but again, you are limiting your options, or limiting, what if you are really off, or, you miscalculate it for some reason. So we've been dealing with the area of descriptive statistics. And again, we've been talking about and using point estimates. The other branch of statistics that we learn about in Stat 1401 is inferential statistics. Inferential is the adjective form of the verb infer. And it has the sense that we're going to make a general or a generalization about the population, but that generalization requires us to make some assumptions. Assumptions made. Okay, so this is where, again, the whole idea of statistics is we take what we learn about a sample. We can describe the sample. We can determine how many are in the sample, the minimum, the maximum, the mean, the median, the mode, and all that. But then what we want to do with that information is we want to be able to apply or infer or generalize that information back to the population, because ultimately the population is what I really want to know about. So that idea of making the inference or that general statement using what we know about the sample, and making that general statement about the population is the area of inferential statistics. Now, it's also true that you can't really do inferential statistics without descriptive statistics. So there is that connection between the two. But again, if I'm using that point estimate, that really small value, or that single value, again, I don't have any leeway for possibly being off or wrong. And so tonight we're going to begin talking about what are called interval estimates, which gives us a range of values between which the population parameter could fall. In terms of a visual, with an interval estimate, it's like you have a little bit of a bigger target to aim for. Okay, instead of one little speck, you have a bigger area at which to aim when you are estimating the population parameter. Our focus in terms of the population parameter in this course is going to be the mean or the average. We could also create confidence intervals or interval estimates for the standard deviation. Those are the two primary parameters, but we could do it really for any of them. The two most popular, again, are the mean and the standard deviation. Our focus in this course is only going to be on the mean. So that's the idea of why we want to create interval estimates. Okay. So a confidence interval, whoops, I messed myself up. A confidence interval is simply another type of estimate, but again, instead of being just a single number, it is an interval of numbers. Okay, you kind of get that sense because of the word interval, and it gives us, again, that range of reasonable values in which we expect our population parameter to fall. Now, even though we have that expectation, there's no guarantee, but we have a predictable probability of success, or in other words, confidence. There is that level of probability where we can say, without a doubt, you know, at 95, we're 95% sure that we're going to fall in this interval, or we're 99% sure. Okay, we can never really truly be 100% totally sure, but we can have that predictable probability of success. Really, any confidence interval, whether we're talking about the Z interval, the T interval, or the proportion, which we will talk about all three tonight, all of them take on the same form. You have your point estimate, which for us is going to be the mean. Okay, so we take that single value that we've been calculating, and then we add or subtract the margin of error. You know, how much could we be off? Okay, so that's the idea of how we create the interval. You take the point estimate, that single value that we've been calculating, and we add and subtract the margin of error. Now we have to use some fancy language and stuff, and there's a few things, other things we got to talk about. Okay, so I wanted to kind of give you an idea. The margin of error is also sometimes called the error bound for the population mean. Okay, the margin of error, which is kind of what you hear, like if you see a news report like the one that I have the diagram for here from 2016 presidential primary. NBC News and the Wall Street Journal had done a poll to kind of see who was going to, you know, what percentage of the population was going to vote for a particular candidate. And if you'll notice at the bottom, it says plus or minus 4.8%. That plus or minus 4.8% is the margin of error for that particular survey. That is how much those percentages could be off. So that's one of the uses that you see of a confidence interval. I see it a lot on news reports, especially when they're doing some sort of survey. You'll see plus or minus 3%, plus or minus 4.8% as it is here. Again, that gives us the margin of error. They typically use the phrase margin of error kind of for so that everybody, every John Doe, every person can understand it. If they used the fancy statistical language, error bound for the population mean, people might kind of scratch their head and not know what they're talking about. Error bound for the population mean is abbreviated EBM. Error bound for the population mean. it's calculated, and you're not going to calculate it by hand. Minitab is going to do it for us, but the margin of error looks at your confidence level and the adjusted standard deviation such that we apply the central limit theorem. Now again, Minitab is going to do that for us. We apply the central limit theorem because again, we're going to be looking at groups of things instead of an individual. But Minitab is going to do that calculation for you. So don't get caught up in that. The confidence level, we talk about the confidence interval. The confidence interval is based on the level of confidence we have. The level of confidence, or the confidence level, is the probability that the population parameter is within the given interval. Again, we typically think about it as the probability of success. Success is my mean, my population parameter falls, within that range of numbers. So the confidence level we think about as being the probability of success. It is typically stated as a percentage, although remember, probabilities can be stated as fractions, decimals, or percents. The confidence level, which is a probability, is typically stated as a percentage. And feasibly, the confidence level could be anywhere from 0% to 100%, because we learned a couple of lessons ago that all probabilities are between 0 and 1. Probability of 0 means the event is impossible. No way, no how is it going to happen. And 1 implies that it is certain, without a doubt, it is going to happen. If we're trying to be confident that our population parameter falls into that particular range of values, I really kind of want to have a high number because I want to be reasonably confident. I don't want to miss it. I want to hit the target. The most commonly used confidence intervals are 90%, 95%, and 99%. You see 99% a lot, especially in the medical field when you're doing medical research, perhaps on a drug trial, because you want to be sure that you're not wrong about whether or not the medication works. 95% of those three, 95% is probably the most popular. It's the one you'll see most often. I wanted to kind of share with you some examples of where confidence intervals are used in the real world, if you will. So in biology, we can use confidence intervals to estimate the mean height, weight, width, diameter of different plants or different animal species. I mentioned clinical trials when you're doing research, or especially related to medicine. It can be used, I've got the yawns all of a sudden. It can be used to determine the mean change in the blood pressure or the heart rate or the cholesterol when taking a particular medication or following a specific diet or doing exercise, whatever that may be. It's also used in marketing and advertising by companies to determine if a particular advertising technique or method or tactic provides higher revenue, which then increases your profit. Manufacturing and engineering. Engineers use it to determine if a new process perhaps works better than a previous process, or that the new process leads to fewer defective parts than the old process. So again, there's a variety of uses of confidence intervals in the real world. So that kind of gives you an idea of what is a confidence interval. It's a range of values in which, between which the population parameter falls, and we have a predictable probability of success. And again, there are really three different types of confidence intervals that we're going to focus on. Again, we're focusing specifically on the population parameter of the mean, but then there's still three different confidence intervals that you could encounter. And the first one is the Z interval. Okay, the Z interval. The Z interval is used whenever you know the population standard deviation. And typically in the problems that you're going to be seeing in this course, in the quiz or on the midterm, you will be given in the problem the population standard deviation. Now, I failed to tell the other class this yesterday or on Tuesday, so I want to backtrack. The Z interval is based on the normal, sometimes it's called the Z distribution. And we just recently talked about that normal distribution. Remember, the normal distribution is a continuous probability distribution that is symmetric with the mean in the middle, and it's bell-shaped. Okay, so we base our Z interval on this normal distribution. So when I begin to read the question, or if I'm trying to decide which one of the intervals I should create, should I do a Z, a T, or a proportion? Because those are the three we're going to talk about. Okay, there's some things I can look for. One of the first things you want to be sure to do, and this is true of both Z and T, is that you have a simple random sample. So somewhere in the story, it will probably say something about randomly selected people, or, randomly selected sample. For our purposes, if it's not noted in the scenario, we are going to assume that it is. Also, we want to consider the sample size is greater than 30, or the population is normally distributed. This goes back to, again, this normal distribution. Remember, I'd mentioned the other day in one of the other classes that when our sample size is 30, that's kind of the magic number. And at 30, most distributions begin to mimic or approximate the normal distribution. So if we have a sample size that's greater than or equal to 30, but I don't know for sure whether I have a normal distribution, we can apply the central limit theorem. By applying the central limit theorem, we force whatever distribution we have to be normal. If I have a sample that is smaller than 30, but I know the population is normally distributed, I'm still good to go. So I either have to know the population is normally distributed, and at that point, I don't care what the sample size is, or I have to know the sample size is greater than 30. Okay, so we kind of check for those two conditions. Again, we kind of assume that those two conditions are met in the scenarios that we're going to be looking at. It's important that you read the scenario from beginning to end, paying very close attention to the information that you're given. The information that you're given is going to determine which of the three types of intervals you're going to create. For the Z interval that we're focusing on at the moment, you would be given four things. You're given the sample mean, the population standard deviation, the sample size, and the confidence level. In every scenario that you encounter, you should have those four things or be able to calculate those things if you have the raw data. The problems are presented in two different ways. First, you can be given the sample statistics. Minitab refers to these as summarized. Okay, so in one case, in your paragraph, you're going to be given summarized sample statistics, and those statistics that you'll be given are the sample mean, the population standard deviation, the sample size, and the confidence level. We can also be given the raw data. If I'm given the raw data, I basically get the sample size and the confidence level. But with raw data, I could, should I need to, calculate the mean. Oh, I'm sorry. And here you'll also be given the population standard deviation. But if I needed it, I could calculate the sample mean from the raw data. But again, Minitab is going to do that for us behind the scenes. I have on slide 9, in case you want to write them down, although you won't need them for the midterm, the steps for Minitab. Whether you have summary statistics, which is the instructions in the middle, or whether you have the raw data, which is the instructions on the right. And we're going to be walking through those. We have to calculate by hand using a handheld calculator. We will have to calculate the error bound for the population mean. It's not a difficult calculation. It is the upper bound, which is given to you by Minitab, minus the lower bound, which is given to you by Minitab. I get the answer and divide by 2. And lastly is you need to know how to correctly interpret the confidence interval. Your interpretation, you could word it, I suppose, differently, but your interpretation should always contain your confidence level, what population parameter you are estimating, and the confidence interval itself, both the lower bound and the upper bound. The phrasing that you're going to see me use pretty much every time, all the time, is the one that's in blue here. We estimate with percent confidence that the true population mean, then you got to put it back into the context of the problem. The true population mean age is between lower bound and upper bound, and you would put the units, whether that's years or inches, whatever it might be, okay? Some of you in the past have tried to get fancy with your wording of the conclusion or the interpretation. My suggestion is you stick with what Miss Ralston has said. Okay, then we're going to get into some examples. I will tell you as we're going through this, and I hope that you're making notes, because mini project number 2 has you calculate confidence intervals, calculate and interpret confidence intervals. So this is what mini project 2 is going to cover. So I have some examples here, and I'm going to go out to my piece of paper where I can highlight and mark things as we go through the example. So this is an example of a Z interval. Now, I know that's the case because that's what we're talking about right now. But let's read it, and I'm going to show you how you know, excuse me, without a doubt, that we're going to do a Z interval. So the question reads, noise levels at, I got a typo, at area hospitals were measured in decibels. The mean of the noise levels in 84 hospital corridors was 61.2 decibels. The population standard deviation was 7.9 decibels. Find the 99% confidence interval for the true population mean. The first thing that jumps out at me to know that I'm doing the Z interval is that in this scenario, very clearly, I am told the population standard deviation. Okay, so I know that I'm going to do a Z interval because I know the population standard deviation. And so if I'm doing a Z interval, Ms. Ralston said I needed 4 things. I need the sample size, I need the sample mean, I need the population standard deviation, and I need the confidence level. And again, all 4 of those things are clearly identified in the problem. I've already indicated the population standard deviation is 7.9. I have that highlighted in yellow. If I go back and read, it says the mean of the noise levels in 84 hospital corridors. Now, I do notice it doesn't really say 84 randomly selected hospital corridors, but I'm going to assume that those corridors were randomly selected. So my sample size is 84. My sample mean, it says the mean of those 84 hospital corridors was 61.2 decibels. So my sample mean is 61.2. And finally, I need to identify my confidence level, and it says find the 99% confidence level. So once I know these 4 things, which I have identified from the scenario, I am going to go out to Minitab to do the calculations. Minitab's going to do the rest of the work for me. Okay, so I'm going out to Minitab. Working through the steps, which are on slide 9. I have to wait for it to update. We go to Stat, Basic Statistics, 1 sample Z. We decided we were doing a Z interval because we have the population standard deviation. So Stat, Basic Statistics, 1 sample Z. We have the summarized data. So I change my option to summarize data. I then have to give it the sample size, okay, which was 84 corridors. The sample mean was 61.2, and the known standard deviation. Minitab refers to the population standard deviation as known. Okay, so Minitab calls this the known population, or excuse me, the known standard deviation. It doesn't use the word population, but it's known standard deviation, which was 7.9. So we're going back to Minitab. 7.9. I then am going to choose options, and it said construct a, what did it say? 99%. So I need to change my confidence level to 99. The alternative hypothesis will always stay the mean does not equal the hypothesized mean. So you don't have to worry about changing that part. I then click OK, and I click OK again, and in the top half of my screen, my results appear. Okay, and I'm going to copy these over to my paper. Okay, a couple of things here just to kind of point out. Minitab shows me the sample size. So N is my sample size. It gives me the sample mean, which I was given, so I can verify that I didn't mistype it. I don't really need the standard error of the mean. And then it gives me the 99% confidence interval for mu, which is the mean. So we have 58.980, comma, 63.420. So in that set of parentheses, you have the lower bound. Okay, so the lowest possible value for the population mean would be 58.980. The second number is the upper bound. And so the highest value that your mean could be is 63.420. I then have to calculate the error bound for the mean. Okay, Minitab does not calculate it directly for me, but gives me the information that I need to do it. The formula for the error bound for the population mean is the upper bound minus the lower bound and that's divided by 2. It is a simple plug and chug calculation. So my error bound for the population mean is 63.420 minus 58.980, and that's divided by 2. I'm going to use my handheld calculator to do the subtraction in the numerator first. 63.420 minus 58.980 is 4.44 divided by 2 is 2.22. So the error bound for the population mean, my margin of error, if you will, is 2.22. So roughly 2 points. Then the last step is to write the conclusion. And again, I would think it would benefit you greatly if you stick with the format that I gave you. So we would say, we estimate with 99% confidence that the true population mean, what were we talking about? Mean noise levels. Mean noise levels in hospitals is between 58.980 decibels and 63.420 decibels. Okay, so as I wrote the conclusion, I filled in the blanks. I filled in my percentage. I filled in what my variable was. It's the true population mean of the variable. My variable in this example was noise levels in hospitals. And then I included the lower bound and the upper bound with the units of measure. I didn't just put 58.980. I included that we were talking about decibels. Okay, questions before we move to the next example? Okay, again, the next one, I also know because I wanted to do an example where you had the raw data that this is a Z interval. But if we read the problem, it says, suppose scores on pop quizzes in statistics are normally distributed with an unknown population mean and a population standard deviation of 2 points. A random sample of 22 scores is taken and are listed here, and you have a list of 22 numbers. Find a 90% confidence interval for the true population mean of statistics pop quiz scores. Okay. So again, as I'm reading this, one of the things that jumps out at me is that it gives me the population standard deviation. So again, that is my clue that I'm going to do a Z interval because I know the population standard deviation. The other thing that is different about this problem is that it gives me the raw data. See, it gives me this list of numbers. This list of numbers is the raw data. And typically when we have the raw data, we're going to be given the sample size, or I can figure it out. It does tell me here that I have 22 scores. If I didn't know that, I could count up how many I have. Okay, so I'm told that my sample size is 22. I don't know the sample mean. It doesn't give that to me. My population standard deviation is 2, and I want to do a 90% confidence level. Now, I don't know the sample mean, but I don't need it to work the confidence interval since I have the raw data. So again, at that point, I am going to go out to Minitab. And I have a little bit extra work to do because I have to enter the raw data into Minitab. So in column 1, I'm going to put the statistics pop quiz scores. Okay, so I have written those down. We have 1, 2, 3, 3, 4, 4, 4, 4. Oops, 4 is only 3 times. Sorry. 5, 5, 5, 5, 6, 6, 6, 6, 7, 7. Whoops. 7, 7, 8, 8, 9, and 10. I notice that I stop on the 22nd row, which again lets me know that I've entered 22 values, which is what I should enter. I'm going to scan it to make sure I didn't do any more typos like I thought I had, or I had. Okay, so it looks like I'm okay. And now I'm ready to find the confidence interval. We have our data in column 1. So again, we go stat, basic statistics. We're again doing a 1 sample Z because we know the population standard deviation. And this time I have 1 or more samples each in a column. So I have my column of data is column 1. I have to enter my population standard deviation known, which was 2. I choose options. I want a 90% confidence level. Again, my alternative hypothesis is not equal. Leave it alone. I click OK and OK. And again, the results appear in the top of the screen. I've copied them so that we can again talk about them. Okay, again, on my results, Minitab indicates that we had a sample size of 22, it actually calculates the sample mean. Remember, I told you in the original problem that it didn't give me the sample mean, but I didn't need it. But Minitab calculates the sample mean for me. It also calculates, and again, I don't need it in this problem, but it calculates the sample standard deviation. And notice that that sample standard deviation is different from the population. And likely it will be because it's based on these 22 numbers. And then again at the end, it gives me my confidence interval. So I have my lower bound is 4.799. My upper bound is 6.201. I then have to calculate the error bound for the mean, population mean. It is upper bound minus lower bound divided by 2. So I have 6.201 upper bound minus the lower bound 4.799 and then divided by 2. Again, please be careful. Make sure you do the subtraction in the numerator first. So I have 6.201 minus 4.799, which is 1.402, and I divide by 2, and I have 0.701. So my margin of error is about 7/10. And finally, I write my conclusion. We estimate with 99, or excuse me, not 99, this was 90, with 90% confidence that the true population mean statistics pop quiz score is between between, lower bound comes first, 4.799 and 6.201. We can assume those are points. It doesn't necessarily say that in the problem, but I can make that assumption. And there you go. Sometimes, going back to this PowerPoint, sometimes when we're looking at these problems, we kind of want to work backwards. Okay. We want to make sure that we have enough data to use in our analysis, because if I don't have a big enough sample, then my results really don't mean anything. So oftentimes we need to make sure we collect enough data from the beginning. And so with confidence intervals, I can say, well, okay, I want to have, you know, a particular margin of error. I want to be within 2 points, or I want to be within a half point, or whatever. So I can establish a particular margin of error. And if I know the population standard deviation, I can then determine what size sample I should collect. Now that also involves a critical value, which is based on the confidence level. And because our confidence level for Z is based on our normal distribution, that lovely continuous bell-shaped curve with the mean in the middle, we have to allow for the possibility that our estimate could be too low, so it'd be on the low end in the left tail, or we could be too high and be on the right end or in the right tail, so that you have what they call a critical region on either end. And so that's why you see this funky notation. It's the letter Z, and then it shows that we're going to do alpha divided by 2. We haven't really talked about alpha, but alpha represents the probability that I'm wrong, or the probability of failure. And we'll get to talk about that a little bit more later, but that's why you see that funky notation. I'm going to give you a table with those numbers on it so that you don't have to memorize them, and that table is provided on the midterm exam, so you don't have to memorize these. But I have the formula here for calculating the number or the sample size that you need. The other thing that we do is we always want to round up. If our answer is not a nice, neat whole number, I'm going to always round up, regardless of the decimal, because we want to ensure that we have enough in the sample. So on the next slide, I have those Z alpha divided by 2 confidence intervals. So I've given you a variety of confidence levels. Again, the 3 most popular are 90%, 95%, and 99%. And so the value for that Z that you're going to use is the value in the right-hand column. Again, I don't want to get too technical with it. Okay, so we're going to take a look at an example of calculating the sample size. Now, again, this particular sample size is related to a Z. Okay, it's related to a Z interval. And again, if you read through the problem, which we'll do in just a minute, but again, it gives you in the story, it does leave out the word population standard deviation, but I'm going to assume that it is, okay, that the population standard deviation is 1100. So again, this is related to the Z interval because I know the population standard deviation. And again, this problem is related to finding the sample size. And guys, this is going to be a hand calculation, something you're going to do with your calculator. So it says, a researcher is interested in estimating the mean monthly salary of sports reporters in a large city. She wants to be 95% confident that her estimate is correct. Assume the population standard deviation is $1,100. How large a sample is needed to get the desired information and to be accurate within $150. So again, if you go back to those slides, I told you when you're looking at sample size, you obviously don't know the sample size because that's what you're looking for. You need the confidence level. you need the population standard deviation, and you need your error bound for the margin, or your margin of error. Okay, so my confidence level here in this problem, it said she wanted to be 95% confident with a population standard deviation of 1100, and she wants to be accurate within $150. The confidence level is important because that confidence level leads us to the critical value that we need in the formula. So if I go back and look at this table, okay, my confidence level is stated in the problem as 95%. Therefore, my critical value is 1.96. So my critical value, the Z alpha divided by 2, is 1.96. I'm then going to substitute into the formula, and I'm going to double check my formula so I make sure I write it down right. It is Z times the population standard deviation divided by the margin of error, all squared. Okay, so my formula, and again, the formula is one of the ones I asked you to write down. N is the Z times the population standard deviation divided by the error bound margin, all squared. So at that point, I have all of the information. It becomes a plug and chug. I have 1.96 times 1100, which is my population standard deviation, divided by 150, and then I'm going to square it. Okay, so I'm going to use my calculator and do all of that at one, and not at one time, but I'm going to do 1.96 times 1100 divided by 150. I get the answer and square it. Which gives me 206.5927111. Okay, so regardless, which it would round up based on the way this one's laid out, but regardless, I'm going to round up. I would need to sample 207 sports reporters in order to have enough to be 95% confident within $150. I would have to survey 207 sports reporters.
Is there a way you can go over the critical value one more time?
How I found it, or what it is?
What it is and how you found it? Because I see how, but I don't really see, I can't really understand all the symbols you got.
I'm not sure I'm understanding what you're asking me. I don't want to delve into that critical value too much because it's a lot of theory that you don't really need to know. The primary thing you need to know is how to get it off of this table.
All right. Now I see
John,
what you were talking about. Yeah, I see it now.
okay, because I'm at 95%, and I just read that number off the table, 1.96. But I got to that point because in the problem, it told me my confidence level was 95%. So I went to this table and found my confidence level of 95% that was given to me And then from there, I just read directly over and found that my critical value was 1.96. Jean, are you okay?
Yeah, I see it now.
All right. Moving along. That finishes Z, okay, and kind of the overview. And I hope the other parts will go a little bit faster. Because it's the same idea, but the second type that we look at is where the population standard deviation is not known. For example, if we look at the next example that I have on this page and we read through it, suppose that a committee is studying whether or not there's a waste of time in our judicial system. It is interested in the mean amount of time individuals waste at the courthouse waiting to be called for jury duty. The committee randomly surveyed 81 people who recently served as jurors. The sample mean wait time was 8 hours with a sample standard deviation of 4. Construct a 90% confidence interval for the population mean time wasted. But notice in this problem, nowhere does it mention a population standard deviation. So there's no mention of it really should be the population standard deviation. So I cannot do the Z because I do not know the population standard deviation. That is the difference. What I do know is the sample standard deviation. It tells me the sample standard deviation. When I know the sample standard deviation, I'm going to construct what is called, and let me do it a different color, what is called a T interval. We use the T interval because I know the sample standard deviation. Now, the process of calculating it, the process of finding the error-bound margin, and the manner in which the conclusion is written are all the same. What changes is the command in Minitab and some of the information you're given. Okay, so for example, for the T interval, we still want to know that we have a simple random sample, a sample size of 30, or that the population is normally distributed. Again, we get different information. We get the sample mean, the sample standard deviation, that's what makes it a T interval, the sample size, and the confidence level as a percentage. Okay, the other thing that I want to point out is that the T interval is based on what's called the student's T distribution. It's a different statistical distribution from the normal. It's very similar to the normal. In fact, it has pretty much all of the same characteristics. It is continuous, just like the normal. It is symmetric, just like the normal, and it's bell-shaped. So when you look at it, and I'm going to draw it intentionally this way, when you look at it, it looks very much like the normal distribution. And if I were to draw two side by side, and I'm hand drawing them, so you're probably thinking, well, she's just doing that. But if we Googled them, you could see the difference. But the biggest difference between the Z and the T is that with the T distribution, you actually have more area, which in a sense means you have more probability, because remember, area corresponds to probability in the tails. For the student's T distribution, that normal bell-shaped curve does not taper or does not go to or get close to the x-axis as fast as the normal. So that's the key difference. And the student's T distribution was originally designed to be used with small samples, specifically samples that were less than 30. So again, the T interval is based on the student's T distribution. And again, I have the keystrokes for Minitab. Again, the primary difference is we're going to choose the command one sample T instead of Z, but everything else is pretty much the same. The formula for the error-bound margin is the same. The interpretation is the same. Nothing changes except the command and the fact that we're going to do a T because we know the sample standard deviation, not the population standard deviation. So again, we still need four things. We need the sample size, we need the sample mean, we have the sample standard deviation, and we need the confidence level, all of which are given in the problem. So it says we randomly surveyed 81 people. The sample mean wait time was 8, and the standard deviation was 4, and we want to construct a 90% interval. All of that information is given in the problem. Just like it was before, the difference is you get the sample standard deviation. Then again, we're going to go out to Minitab. We go Stat, Basic Statistics, one sample T. Again, we have summarized data. My sample size was 81. My sample mean was 8. The standard deviation, notice it no longer says known. Now it's just called plain old everyday standard deviation. It's 4. Again, I go to options. I want a 90% confidence interval. Again, my alternative hypothesis remains at not equal. I hit OK, OK, and I get my results. Again, you kind of get the same information that you got previously. You have your sample size, you have your sample mean, your sample standard deviation, and then at the very end, you have your confidence interval. So I have 7.260, comma 8.740. Again, the first number is your lower bound. The second number is your upper bound. That hasn't changed. We then calculate our error bound margin. Okay. Again, that's going to be the upper bound minus the lower bound divided by 2. So I have 8.740 minus 7.260 all divided by 2. Again, make sure you do the subtraction in the numerator first. 8.740 minus 7.260 is 1.48 divided by 2, which is going to be 0.72. So my error bound margin is about 72 hundredths. We then write our conclusion the same way we did before. That has not changed. We estimate with 90% confidence that the mean amount of wasted time is between 7.260 hours and 8.740 hours. Please do not try to get fancy with the words. Use the statement that I have provided on the slides. You are less likely to make a mistake that way. I'm concerned that I'm going to run out of time, so I'm going to skip the next one, but you can also, with the t-interval, be given the raw data. But here again, you should recognize it as being the t, because if you read through this statement, nowhere in this story does it mention the population standard deviation, nor does it mention the sample standard deviation, but I have the raw data. This raw data is my sample. So I could calculate the sample mean and the sample standard deviation if I needed to. But again, I don't need to calculate the confidence interval because Minitab is going to do it for me, just like I did before, except I'm going to choose one sample t for the command. Guys, don't overthink it. It's the same process, the same thing. It's just a matter of, are you going to do Z or are you going to do T? And it comes down to, do you know the population standard deviation or not? We do not do sample size estimations for T intervals. We do not do sample size estimation for T intervals. We've got 30 minutes left, and we've got one more type to talk about. And it looks a little scary because the notation is different, but honestly, it's the same thing. Okay, we're going to talk about confidence intervals related to a proportion or a percentage. Okay, it's kind of the same idea. The first two related to the mean. Okay, but now we're going to look at where it relates to proportions or percentages. And again, the process is the same. The formulas are a little different. And then you have to be able to identify that you're dealing with a proportion. Well, there are two things you can look for. One is there is no mention in the scenario of mean or average. And secondly, there is the mention of a proportion or a percentage. The confidence interval for the proportion is based on the binomial distribution. And again, I don't want to get real technical about the binomial distribution. We've talked about it briefly before, but we actually do. The binomial distribution can be approximated using the normal. So we actually use an approximation via the normal distribution, where you have that nice continuous probability distribution that's bell-shaped and symmetric. So don't get too caught up in that. But again, I just mention it here in case somewhere down the road someone asks you about it. But the confidence interval for proportion is based on the binomial distribution, okay? But we use the approximation via the normal distribution. No big deal. Goes on behind the scenes. The notation does change slightly, again, because we're talking about a percentage or a proportion. So our point estimate is no longer the mean. Our point estimate is the proportion. And the way we distinguish it from the true accurate proportion, okay, if we were writing the true population proportion, we would actually just use the letter P. Well, to be the point estimate, to indicate that it's an estimate, we put a little tick mark next to the P. It's read P prime. And again, that little tick mark indicates to the researcher, to the reader, that this is an estimate versus the true. Also, you have to go back and remember a little bit that from the binomial distribution, remember P is the probability of success, that you get what you want. Q is the probability of failure, you don't get what you want. And together, those two values total to 1. Okay, because then you have Q prime, and Q prime, and I got a typo here, is 1 minus P prime, because P and Q together have to add to 1. We also, instead of having the error bound for the mean, we're now dealing with a proportion. So it becomes E, B, P for proportion, error bound for the proportion. But its calculation is the same as before. It's still upper bound minus lower bound. On slide 5, I have the Minitab instructions. And in these problems, you're given the number of successes, which is X. Minitab refers to that as the number of events. The sample size is given as N. Minitab calls that the number of trials. And then, of course, you have your confidence level. And those are the only 3 things that I need to work the problem. Typically with these type problems, we only deal with summarized statistics. We don't usually have the raw data. We could, but we don't usually. Okay, then you have again your Minitab steps. Again, the primary difference here is that you're going to choose one sample proportion, and then you also have to indicate that we're doing a normal approximation. It's one little extra step there. Conclusion is written in the same format. We do change it to say true population proportion instead of mean, because we're talking about a proportion. Again, don't overthink it. It's the same process. It's just that you have different information, so you have to use the different command or know that you're calculating it in a slightly different way. Again, if I'm looking at this problem and I read through it, it says, suppose that a market research firm is hired to estimate the percent of adults living in a large city who have cell phones. 500 randomly selected adult residents in this city are surveyed to determine whether they have cell phones. Of the 500 people surveyed, 421 responded, yes, they have cell phones. Using a 95% confidence level, compute a confidence interval estimate for the true proportion of adult residents of the city, who have cell phones. Okay, so reading that whole story, nowhere did I mention mean or average. So there's one clue. The second clue that I'm going to do a proportion is in the first sentence, it does talk about a percentage. Okay, so it does talk about percent. So again, that's my clue that I'm going to do a Z interval for a proportion. And to do a Z interval for a proportion, I need three things. I need N, which is the number of trials or the sample size. I need X, the number of successes that I got what I want, and the confidence level. So it tells me in the story that 500 people were surveyed. So my sample size is 500. Of those, 421 responded, yes, they have a cell phone. And I have a 95% confidence level. Going out to Minitab. Okay, so at this point, we go to Minitab. Stat, basic statistics, one proportion. We determined we needed to do a proportion because the problem talked about percentages. So one proportion, and I have summarized data. The number of events was 421. That was 421 people who said, yes, they have a cell phone. There were 500 trials. We choose options. We want a 95% confidence interval. My proportion does not equal, and we want to do a normal approximation. Okay, so that's the piece you have to change. You have to change it from exact to normal approximation. I click OK. OK. And again, in the top half of my screen, it gives me my results. Okay, so Minitab, a couple of things here about this printout. It gives you, again, N, which is your sample size. It does indicate the number of successes, but Minitab also calculates P prime. The sample P is P prime. That is your point estimate. Minitab calculates that for you. It then gives you your interval. My interval here is 0.810030, comma 0.873970. It gives you the results. Your results are decimals, or excuse me, let me write it this way. That result is a percentage written as a decimal. So remember, I can convert from a decimal to a percentage by multiplying by 100, which apparently some of you had difficulty doing on project 1. So we'll talk about how to do that in a minute. I still need to calculate the error-bound margin. Same formula, upper bound minus lower bound divided by 2. Okay, so I have 0.810, oops, wrong value, sorry. 0.873970 upper bound minus lower bound, all divided by 2. Okay, so we do the subtraction. 0.873970 minus 0.810030, which gives me 0.06394 divided by 2, which is 0.03197, which again is a decimal value. Should I want to convert that to a percent, I'm going to multiply that decimal by 100%, which gives me 3.197%. We then write our conclusion. We estimate with, what was it, 90 or 95? 95. With 95% confidence that the true population proportion, I need to indicate what kind of proportion it is, proportion of adult residents of the city own a cell phone, or who own a cell phone, is between, and I want to state them as percentages, so I would have 87.3970% and Or I should put the lower one first. Sorry. 81.003% and 87.397%. Now, guys, you should be able to take a decimal and convert it to a percentage. 837,970 times 100% is 87.397. You can add the 0 at the end, but you don't need it. If you cannot multiply that by 100% in your head, get a calculator. Same process, but you're talking about it with respect to percentages or proportions instead of the mean. We also can calculate the sample size. Again, because we're using the normal distribution, we have the same table that we had before, where you have your confidence level in the left column, which is going to be given to you in the problem, and then you have the corresponding critical value in the right. And again, I can use this same table because I am using the normal distribution to approximate the binomial which the confidence interval for a proportion is based upon. The formula is slightly different. You have to have your critical value, you square it, multiply it times your point estimate for success, times the point estimate for failure, divided by your error bound for the percentage or your margin of error squared. Different formula, same thought process. Everything is given to you in the problem. Well, I don't think Q is, so we have to calculate Q. So the problem says, suppose a mobile phone company wants to determine the current percentage of customers aged 50 or older who use text messaging on their cell phones. How many customers aged 50 or older should the company survey in order to be 90% confident that the estimated sample proportion is within 3 percentage points of the true population proportion of customers aged 50 or older who use text messaging on their cell phone? Now, here again, you got to remember that you got to deal with the sample size for proportions. But again, nowhere in that problem does it talk about the mean or the average. In fact, multiple times it uses the word proportion. It also uses the word percentage. So that should be the red flag blinking in your face saying that we want to do, I gotta get my mouse over here, the sample size estimate or estimation for a proportion. Well, to do that, I kind of need the same 3 pieces of information that I had before. I need my confidence level. I need either P prime, which is my sample point estimate. I need Q prime, and I need the error bound for the proportion. Okay, so if I read through this problem again, let me see, kind of scan it here and see what I got. Okay, in order to be 90% confident Okay, so my confidence level is given in the problem as 90%. It says we want to be within 3 percentage points. Okay, 3 percentage points. So my error bound for the proportion, error bound for the proportion is 3%. And that's really all the numbers they give me. They don't give me a value for the point estimate or the sample proportion. Okay, here's the deal. If you don't know P and Q, we're going to use 0.5. Okay, if P and Q are not given, if no point estimate is given, we will use 0.5. We got a 50-50 chance of a success and a 50-50 chance of failure. Remember, P and Q have to add to 1. Okay, so then I'm going to substitute into my equation or the formula. The formula is my critical value, which we'll have to look up in a minute, squared times P prime times Q prime divided by the error bound proportion squared. A couple of things that I discovered when working with this formula earlier is you want this error bound proportion as a decimal. So it's given to me as 3 percentage points, but 3% written as a decimal is 3 divided by 100, in case you forgot your math, which is 0.03. To get to the critical value that I need, we do the same process. My confidence level is 90%. So that's going to lead me to my critical value, which is Z alpha over 2. So I'm going back to the table. In the left-hand column, I find my confidence level, which was given 90%. And the value that I need is 1.65. Okay, so my critical value from the table is 1.65. From there, it becomes a plug and a chug. We're going to put the numbers in there and see what we get. So I have 1.65, that's my critical value squared, times my point estimate for P, which is 0.5, times the point estimate for Q, which is 0.5, divided by my error bound proportion squared, written as a decimal. Okay, I'm going to do all the calculations on my calculator. 0.03 squared is 0.0009. Okay, so then I'm going to do the numerator. 1.65 squared times 0.5 times 0.5 equals 0.68065 equals. So 0.680625 divided by 0.0009 gives me 756.25. So again, we always round up. So that would be, they would need to survey 757 people aged 50 or older. Okay. They would have to survey 757 people aged 50 or older. Questions? All right, here's what you got going on. Quiz 6 is due by Sunday, which is October the 2nd. The midterm will open on Monday, October the 3rd, and will remain open through Saturday, October the 8th at 11:30 p.m. You have to take it in one sitting. You cannot start, stop, start, stop. Once you sit down and open it and begin, you have to finish it. So you need to allot at least 2 hours. If at 2 hours, if you're not finished, it's not going to cut you off. Okay, it just notifies me that you took longer than 2 hours, but the allotted time is 2 hours. Again, I would strongly encourage you to look over the midterm study guide that is attached to the announcement for week 7. And if you have questions, you need to send an email. You could post it. You could send an email. You can come into Zoom on Thursday between 2 o'clock and 4 o'clock, or between 8 and 9 p.m. on Sunday. We will have class next week, so I suppose if you're not going to take the midterm before then, you could ask questions at the beginning of the class next Tuesday. Also, you are now ready to do project number 2. The instructions are provided. You may very well want to read through those instructions so that if you have questions, you can ask. Let's not have another fiasco when I have to grade these submissions. The project 2 is due on October the 10th, which I believe is a week from Monday. So you all have almost 2 weeks to do it. So I would suggest that you look at those instructions before class next Tuesday as well, so that if you have questions about it, you can ask them during the class session or come in to the Zoom office hours. Okay, any questions?
You said that we could use a one sheet of paper. Does it have to be written, or can it be like typed, or does it matter?
I think it says handwritten on the notes, but if you type it, it's fine. But you probably, JD, on the respondus, it'll ask you to hold it up and show it.
Okay.
Okay, because you do have, I mean, I've noted, I put in the instructions that you can have one so that it won't think that you're cheating when you're looking at it.
Okay, sounds good. Thank you.
Other questions?